So this is going to be a short talk, lightweight talk about single problem, single technique. So the problem I'm going to talk about is called disjoint paths. We are given a directed or undirected graph and k pairs of vertices, and we ask whether we can connect all the pairs by vertex disjoint paths. So this is an example of an input, so we got to connect red to red, green to green, and so on. This is an example of a solution. And the parameter k is the number of terminal pairs to be connected. So the parameterized status of this problem differs greatly depending on the type of graphs we consider. For undirected graphs, it is famously FPT due to deep results from graph miners theory. But for general directed graphs, the problem is very hard. It's already NP hard for k being 2. So no hope for like any FPT or any kind of this result. And the sweet spot between these two is the case of directed acyclic graphs. So the problem is polynomial time solvable by dynamic programming for every constant k, but it is W1 hard, so unlikely to be FPT. And this last case of DAGs will be I will focus on this one. In the optimization variant, we don't have to satisfy all the terminal pairs, but we want to maximize the number of pairs that are connected by disjoint paths. And it is also pretty hard to approximate in polynomial time. For our case of DAGs, the best known approximation factor is square root of n by a simple greedy approach, and this is tight. It is NP hard to improve it. So what I'm going to talk about is whether can we get some better approximation if we allow for FPT running time. So we are in the realm of FPT approximation, and as you can already guess, we're going to talk about hardness of approximation. And as you saw in the last two days, there are few hardness assumptions on which we can rely when proving lower bounds, and GAP-ETH is the strongest one. From it, it implies ETH, then PHH, and the weakest assumption is just that FPT unequals W1. And as already mentioned, when we start from an assumption like GAP-ETH, we already have a gap, and we just need to widen it. While when we start just from W1 hardness, we need to create a gap to bootstrap our reduction, and this is usually challenging. And this can be done by the framework of distributed PCP or threshold graphs. But here, I'm not going to use any of this machinery we talked about yesterday, but something pretty independent. And the main theorem, like the only theorem I'm going to talk about is this, that for any constant q, it is W1 hard to distinguish whether for a given DAG instance of disjoint paths, whether we can satisfy all the terminal pairs or at most k over q. And as a consequence, there is no q approximation for any constant q. No? And this technique is, one may say, it's motivated by like wise words of a great man who happens to be with us today. So this is going to be a self-reduction. So specifically, we're going to start with an instance of disjoint paths, so that in a yes instance we can serve all the terminal pairs. In a no instance, we can satisfy at most k minus 1 of them, and we want to create a gap in the reduction. So a yes instance should be mapped also to a yes instance, but a no instance should be mapped to such a scenario that we can serve at most parameter over Q paths. And this is in some sense similar to the reduction that, like the sketch of which we saw on the very first talk on Monday, that we can treat our initial instance as some kind of a block, and now we can play Lego with it. We can try to connect instances in some way to make it harder and harder. So here is a toy example. We can make, starting from some initial instance, we can build, like, we can take 2K copies of it and put them into 2 layers and connect the sinks of the first layer to the sources of the second layer. And when I make a connection like this from the sink number 2 to here, then I want to connect in the end this like super source to this super sink. Okay? And of course, as usually, it is easy to show that if the original instance is a yes instance, then the new instance is also fully satisfiable. Like all the, I didn't put like the orientation of the arrows, but like all of them are oriented upwards. So if we can route all the paths in each block, then we can like connect every source to everything. This is easy, and it is always trickier to show that if the original instance is a no instance, then we have some property that allows us to amplify the gap. And what can we say so far in this construction? Suppose that the initial one is a no instance, so we can't serve 3 of them at the same time. So one thing we can say is that we cannot serve simultaneously like the request number 1 to 3, yeah? Because they cannot go through the first block. The same about 4, 5, 6, 7, 8, 9. And also we can't serve simultaneously 1, 5, 8 because they would need to squeeze through that block, which is also impossible. Yeah? So we have 6 tuples of requests that cannot go through together at the same time. Okay, we can iterate this construction by stacking more and more layers. And here for 3 layers, we can just take layer 2 construction, take k instances like that, put them next to each other, and do the same construction. Now we have k square sinks over there, and for each of them we choose some like output box out of new k square copies of the original instance. I didn't put like all the edges in the last row because it would be illegible, but you can imagine them. When you have d layers, then the total number of requests to be served is k to d. And what we would like to say to show, say, a hardness of 2 approximation is that whenever we would like to serve half of the requests, yeah, to connect half of the terminal pairs, this should be, by some reason, impossible. And to certify that some set of requests is infeasible, we will use this notion of collision that we saw on the previous slide. So here, we cannot simultaneously serve all those guys marked as red because 6, 10, and 23 would need to go through this block. And you can convince yourself that there is no other way of serving this triple. Yeah, so our goal is to find this like a connection scheme, how to put those edges between the layers to have such a property that large set of requests would have some collision. And I will show how to construct such a connection scheme in an indirect way by treating this as a game. So the order of events might seem weird for you at the first glance. So that first the player A chooses a set of half of the requests to be served, and then the second player, B, chooses the connections between the layers to form a collision. And player B wins when there is a collision. So, this doesn't look like a legit reduction because we first somehow choose a solution candidate, and only afterwards we finish construction of the instance. And a priori, player B could play adaptive to player A did. So this doesn't seem to give a single instance in the end in our reduction. But here is a trick. There is a lemma that works for sufficiently large number of layers, and it says that when player A chooses any strategy, and then player B chooses the strategy at random according to some distribution, then the probability that A wins, so that there is no collision, is very small. It's less than 2 to minus k to d. And when we have this, then observe that there are at most 2 to k to d possible strategies for player A, because this is upper bound on the number of subsets. And then by a union bound, there is a single strategy for player B that works against every strategy of player A. Yeah? Here I made a picture for that. So when we have a probabilistic space, which is the set of strategies for player B, and we have strategies which fail against strategy A1, A2, A3, and A4. But when the total sum of probabilities is less than 1, then there is some point in the probabilistic space that is not covered, meaning there is some single non-adaptive strategy for player B that wins against every possible strategy of player A. In other words, this strategy of player B gives rise to a connection scheme for which every set of k to d over 2 requests has a collision. And in yet other words, there is a connection scheme for which we can construct our reduction. If the initial instance is no, then the new instance would have a gap of value 2. So far, so good? So now I will move to a sketch of the proof of the lemma. And first, let me say how to formalize this random strategy of player B. We can encode this choice of connections between layers as a family of permutations. For example, like here for the first block, we want to say where the sink number 1 goes. It goes to output box A. The second one goes to C. The third one goes to B. This is encoded in the first permutation over here. Yeah, and these permutations encode all the connections over there. And now we have 3 permutations for the between second and third row, which say when I take 9 sinks over there, to which 9 of those boxes they go. And a collision can be now expressed in such a event that we have k permutations under a common node, and we have k guys which are active, meaning that they were marked by player A, and they are mapped to a single output box. Yeah? This is a collision. In greater generality, the strategy of player B is, can be seen as a full k-array tree of depth D. And for every non-root node, we'll have a permutation mapping the leaves of that guy, being each leaf representing a request. Some of them are marked red, some not. This permutation would map those requests to the output boxes in the next layer. And and the collision occurs if for some node we would map k active guys to the same value. So player B would choose each of these permutations at random independently. So in order now to estimate the probability of having a collision, take a look at the single node. And I will say that node in my tree is rich if for every child of it, the fraction of active requests in their subtree is at least like 1/4. Yeah, so here like I have some like node with 3 children, and the red guys are the guys marked by player A. And the value of this node would be like this number, the number of leaves of the number of requests in a subtree of each child of this guy. So what happens now? The player B chooses k random permutations of sets of size m, and the collision occurs if there is some index for which each permutation maps active element to this index I. Since this node is rich and there is like a fraction 1/4 in every subtree, then the probability that a single permutation maps an active guy to index I is like 1/4, at least. And then the probability that we create no collision for fixed index I is like that. And now these events are not really independent for different i's, but they still they enjoy something called negative association. So we can still upper bound the probability of having no collision by a product of the probabilities. Yeah, and in the end, we get a probability of having no collision, which is exponential in the value of the node, which is like the number of these requests. Okay? So this analysis works for a node that is rich, and how to find a rich guy. So let's start from the root and recall that the player A chose at least half of the requests. Yeah? So the fraction of guys marked red in the entire tree is at least half. Suppose that root is not rich. It means that there is it has a child for which this fraction of red leaves is less than 1/4. But then, like the average of those fractions among the children is also the same as for the parent. It's at least half. That means that there is some other child for which this fraction is strictly larger than half. And suppose that this child also is not rich, then we iterate this argument, also increasing this fraction, and we can't iterate this process too long, because after a constant number of steps, this fraction would exceed 1. This is impossible. So within a constant number of steps, we will find a guy which is rich, and this guy is close to the root, so his value the size of the subtree over here is large. Then we can repeat this process after shaving off this first super layer, and then we look for rich guys by the same argument below, and now the value, their value would be lower, but at the same time we will find more of them. Okay, in the previous slide, I argued that for a ridge node, this probability of having no collision is exponential in its value, and these events for all those nodes of having no collisions are independent. We can multiply them. So when we have multiple ridge nodes with such values, then when we multiply those probabilities, then those values would add up in the exponent. And by this argument, by dividing this tree into those super layers, we can show that the family of all rich guys would satisfy something like this: that the total sum of their value would be roughly k to d, the size of the total number of leaves, times d, roughly, like the number of those super layers. And this additional d is important because now this term goes here in the exponent instead of m. And we need to eat up this factor 4 to k. So we just set the depth of this entire tree, the number of layers, to be exponential in k, so that this d cancels out with 4 to the k. And in the end, we get a total probability of having no collision at most this, like less than 2 to minus k to d, which is what we wanted. Yeah? And the probabilistic argument goes through. Okay, so this is the main theorem restated. Let me also mention that this argument is probabilistic, but the reduction is not. Like this argument just shows the existence of a strategy of player B, and in the reduction we can just iterate over all the possible strategies and choose one that satisfies this property. So this argument gives a constant approximation hardness for FPT approximation for disjoint paths on DAX. And if you adjust this quantity Q to depend on the parameter, you can boost this approximation hardness to slightly super constant. But because of this super exponential blow up in the parameter, like you only get something sublogarithmic. And let me conclude with some open problems that stem from this result. First of all, if we assume ETH, then we can also show a tight running time lower bound for k disjoint paths on DAX. But this reduction I presented, it blow ups parameters like very, very much, and it doesn't preserve such a running time at all. So the question is, what about a constant approximation which is just a little faster than N2K? Second thing is that, yeah, I said that like this blow up of the parameter is very uncontrolled, and the question is, can you refine this construction somehow so this blow up would rule out some higher approximation factors. And finally, and the question I think most interesting to me and to the others is whether this argument can work for some other problems of a different nature. Like so far, it also worked for one more problem, namely Steiner orientation, which is pretty similar in spirit to the disjoint paths. And it seems for now that it is like that you really need this property that you can stack instances of your problem in some sequential way and connect them. So it will be cool to see it works for some like CSP like problems or yeah to derive like some different results from this technique. That's it. Thanks.
Questions? So why do you always need to blow up the K in your construction? Can you, if you increase the depth, can you just keep the K without?
So I had to set the depth of this tree to be exponential in K for this estimation to work. So yeah, like the final parameter is K to D, which would be now K to the 4 to the K. Yeah, this is why it blows up. And if you wonder about like why this is so bad, then like this approximation factor is measured with respect to the final parameter you get. Yeah, so this like this K is the new parameter, which is double exponential in the first one.
So you think that people often like think about allowing congestion of a true or a constant, and then rule out the algorithms or hardness like yeah. Does your work rule out congestion?
Yeah, if you say if you consider disjoint paths with congestion C, then yeah, you can roughly do the same trick. Yeah, like if it's hard to be rooted in a single block with congestion 2, then like those arcs like in between couldn't really help you if you allow larger few paths to go through a single edge. So it works in the same way. But I guess like the more important and another variant of congestion is that you either want to route all the paths without any congestion, or you compromise the congestion to be, say, 4. And if you have such a gap problem, then I don't know if this is FPT or W1-hard.
Does your thing say anything for H disjoint paths?
In disjoint is in directed graphs, like edge disjoint and vertex disjoints are roughly equivalent. There are easy reductions in both ways. There's one caveat that this works in general directed graphs, but not in planar digraphs, because these reductions may break planarity. So in planar graphs, edge disjoint paths is W1-hard, but vertex disjoint is FPT.
Tight, or do you think maybe the same randomized construction actually achieves better balance?
You mean like to avoid this super exponential blow up? I guess so. Like it's very like generous at this point. Like this estimation is very crude. I would guess there is some smarter way to analyze this.
And maybe also some deterministic construction would even be better than randomized.
If you wanted to like show the existence of those connections deterministically, without using probabilistic method, then I guess you would need to use some kind of expanders, and I don't think that this strategy would get you any better bound. I guess you would need to, yeah, like refine it, the idea from scratch.